Hoca. Shantan Hoca is co-founder and CEO of Boston Quantum, and currently he's an ECS PhD student in Engineering Quantum System Group at MIT. He received his bachelor in physics and math at Yale University, where he experimentally demonstrated bosonic quantum error correction codes in Darut Group. Before grad school, he worked as a full-time software engineer and AI privacy and security infra at Facebook, and also founder of UKC Group and Quantum Coalition. As a PhD student, he is eager to further explore bosonic system for quantum information processing. And today he will give a lecture on bosonic error correction codes. Mr. Shantanu, welcome and happy to have you here.
Thank you so much for the kind introduction. I'll get right into it. So, my name is Shantanu, and today I'll be talking to you all about bosonic quantum error correction. And we'll talk a little bit about theory, some experiment. By training, I'm an experimentalist. In our group, we actually build these superconducting circuit processors for bosonic error correction. So we'll talk a little bit about that. And we'll end the talk with a little bit of software, some software packages that we built in the group to aid in our theory and experiments. And we'll talk more about that tomorrow, the software side of it. So let's jump into it. The first section is just to motivate, why we care about quantum computers at this point, probably in the program, and maybe even in your careers. This is well motivated. There are certain algorithms that we've come up with, quantum algorithms that provide much better sort of time complexity than the best classical algorithms that are out there. I think some of the most exciting ones, or some of the most exciting reasons to build quantum computers, are to simulate the fundamental physics of our universe. So, for example, like simulating the caffeine molecule very accurately, I believe is an intractable problem on a classical computer. People come up with, of course, very accurate approximations, but I think it'll be quite exciting to be able to simulate molecules and different quantum mechanical systems on these platforms. And there's a number of other use cases that we can tackle with this really new paradigm of computing. But to do that, we have to build good hardware. We have to build hardware that doesn't just have a large number of qubits, but also has very high quality qubits. Qubits where the information lives for a long time with respect to how fast the gates are. So a metric that I like to think about is basically the lifetime of the quantum information divided by how fast it is to manipulate that quantum information, how fast it is to do single qubit gates or 2-qubit gates. And in a sense, that's kind of like the numbers of lines of code you can write on your quantum computer, right? Before that information decoheres, it's scrambled. And so really what we're trying to do is we're trying to be able to write more lines of code on our quantum computer, run more complex algorithms. And that brings us to what are the kinds of hardware, that we deal with. You might have heard a little bit about different kinds of hardware, probably more focused on superconducting circuits. That's the kind of hardware that I've been working with in my career. And I'm working with at MIT in the Engineering Quantum Systems group. I won't get too much into the hardware, but the kinds of hardware that we use are typically some sort of metal superconducting that goes superconducting like aluminum, that has been that is patterned in some way on some sort of substrate like silicon. And by creating these coplanar waveguide structures, we can create essentially different capacitances, different inductances, and even these nonlinear inductances called Josephson junctions. By putting these capacitances, linear inductances, and nonlinear inductive elements, Josephson junctions, together in different ways, we get different kinds of qubits. And we get a zoo of these qubits, starting with the simplest, the transmon, just replacing the linear inductor with Josephson junction, to shape the potential enough that you can have a two-level system that you can address, go from 0 to 1 and 1 back down to 0. Um, the really cool thing about these systems is um, that we call them artificial atoms, in that we can change the properties of these systems, unlike maybe nature's atoms, which are perfect, which is great in one regard. One atom will be the same as the other atom. These artificial atoms, we can actually change the properties um, of these qubits depending on what we want to do, and so that makes for a very exciting research landscape that's emerged in superconducting circuits. So our quantum computer, superconducting circuit-based quantum computer, is getting better. Right? Well, in general, these quantum computers are getting better. We're able to run more lines of code, so to speak, on more qubits. So that's maybe one metric, quantum volume, that keeps increasing year after year. And really, in if you look across industry and across even hardware platforms, one thing that's quite important, a milestone guiding light for people in the field, is error correction. So being able to create, the holy grail is this, being able to create these universal fault tolerant quantum computers that are in which we can suppress physical errors by um, using, for example, redundancy. And so we'll get into that. That'll be the focus of this talk, error correction. People typically think about topological error correction, register-based error correction, things like the repetition code and the surface code. Today, we'll be talking more about a bosonic error correction. I believe you heard about a few types of bosonic qubits, like cat qubits, for example. And cat qubits aren't necessarily error correcting codes. There are cat codes, but like the simplest cat qubit isn't even error correcting a qubit, but is already quite interesting for its bias properties. So, yeah, let's talk about error correction. So we'll start off with something that I think makes a lot more sense, especially when you come from the classical intuition that we've been building our whole lives. I think the best place to start is with the repetition code and the quantum equivalent of that repetition code, where we're encoding one logical one state as one state across many, a register of many physical qubits. And if gamma rays or other error mechanisms come in and flip, 1 to a 0, in a sense, in the classical repetition code, by majority rule, we can just count all of these zeros and ones, and by majority rule, this is still represents a logical one. In the quantum case, you can't really open the box and look at Schrodinger's cat, and so you can't measure these qubits individually, but you can measure stabilizers. So, for example, you can measure pairwise stabilizers, neighboring stabilizers. And for the 3-qubit repetition code, what this might mean is, let's say the middle qubit flips. Then by looking at the parity of these neighboring qubits, we can identify that an error has happened in the middle qubit, regardless of if we're in the 0 state or in the 1 state. And so that allows us to detect when an error has happened without detecting which logical state we're in. That's really the idea, being able to detect the error without detecting which logical state you're in. There are more complicated error correcting codes out there. This repetition code, for example, just can deal with a bit flip or phase flip errors. And so to deal with both bit flips and phase flips, people construct something called a surface code, where we can actually detect and correct these bit flips and phase flips. And this is something that I played around with when I was in undergrad, just for fun. And I put, this is now quite old, probably, but I put a package out there called Qt codes to simulate these different kinds of topological quantum error correcting codes on Qiskit and on IBM hardware. So I think that was quite fun to be able to actually play around with these codes, simulate them, and understand them. I think there's a whole class of these register-based codes beyond, like the surface code. called these QLDPC codes, these quantum low density parity check codes. And in these codes, they're a little bit more hardware efficient, but they require kind of long range gates between different qubits. But all these register-based codes are similar in that they are storing one logical or like some amount of logical information, let's say one logical qubit, across the joint Hilbert space of many physical qubits. So one logical qubit of information across many two-level systems. And as you add more and more two-level systems, you get this Hilbert space that goes exponentially in size. And by redundantly encoding, your logical qubit, you can actually protect that information. Another way to look at it is you can non-locally encode information across many qubits so that errors, which are local, cannot measure and destroy that information. In bosonic error correction, we do a similar thing. Instead of putting one logical qubit across many two-level systems, we put one logical qubit in the large Hilbert space of a single quantum harmonic oscillator. This quantum harmonic oscillator, you can think of this as like a box in which you can put different amounts of photons. So you could put 0 photons, 1 photon, 2 photon, 3 photons, and so on up to some experimental limit. In theory, you can put as many photons as you want, but in experiment, there's usually some limit. And to control this system, all you really need is a nonlinear system, like a two-level system, like a control qubit. And so the idea is very similar. Instead of having, the space of many two-level systems, we now have this large, intrinsically large space of a quantum harmonic oscillator. And all we need to control this is a control qubit. And so in a sense, it's quite hardware efficient, right? All you need is an oscillator and a control qubit. And so these bosonic codes, they offer a very hardware efficient path towards error correction and fault tolerance. Taking a step back, in reality, one likely roadmap is actually layering these error correcting codes. So for example, creating bosonic qubits in a very hardware efficient way, and then putting those bosonic qubits together into something like a surface code. And so you have these layers of error correction that are kind of like multiplying together to give you that much more fault tolerance and requiring less hardware. So instead of 1,000 physical qubits, you might only need a few of these bosonic qubits within a surface code to get a very good logical qubit, is a statement. I'll quickly stop before I proceed, just to see if there are any questions. And if not, I can keep going.
Yes, thank you. We have some questions I can ask now. Any comments on dual rail qubits? The erasure error is insanely high, but those errors are easier to correct for. And T1 and T2 times are better. Do you see this as a useful trait for larger quantum computers?
Yeah, absolutely. So there's a lot of research going on into how the thresholds, for example, for surface code, and the threshold being the point at which the threshold being the physical error rate below which it's useful to add more qubits to your error correcting code. So if you're above threshold, adding more qubits actually makes things worse. But if you're below threshold, adding more qubits will make things better and will allow you to further suppress your logical error rate. That threshold itself is higher for erasure qubits. And so for sure, erasure qubits are quite interesting in their ability to have be a little bit more lenient to the requirements of the physical qubits we put together into a surface code. There's some great work that I believe this whole workshop kicked off with that Professor Gervin probably spoke about using these dual resonator, dual rail qubits, two resonators, and encoding a single logical qubit of information across these two resonators. Technically, you don't really need to use two resonators. The reason why they use it is, one of the reasons is because these resonators have really nice lifetimes, but you could use other platforms for that. But I think they are particularly interested in that, especially for things like the surface code. Cool. Any other
Thank you
questions?
for your answer. Yeah, you can continue.
Okay. Yeah, so now let's dive a little bit deeper into bosonic error correction. Before we do that, let me just talk about the Wigner quasi-probability distribution because I'll be showing a lot of these Wigner plots. And so I just want to make sure people understand this. So on the right, I show a Wigner quasi-probability distribution, quasi-probability in that, we have these positive and negative probabilities. So it's quasi-probabilities. And the way I like to understand this plot in the center is that if you integrate along these horizontal lines, then what you'll get is the probability distribution in momentum space. And if you integrate down along these vertical lines, then what you get is the probability distribution in position space. And so you can kind of, the reds are positive and the blues are negative. So you can kind of see as this cat state turns around, Schrodinger cat state rotates in phase space, you can see how these probability distributions are evolving in time. So hopefully that communicates a little bit of intuition for these Wigner plots. Okay, let's start with the simplest bosonic error correcting code called the binomial code. In this code, our logical zero is superposition of 0 photons and 4 photons inside our resonator. And our logical 1 is when we have 2 photons inside the resonator. The main error mechanism in these systems is when a single photon leaves the resonator. And so what happens in that case? In that case, we go down from 4 plus 0 down to 3 photons, and from 2 photons down to 1 photon in the logical 0 and the logical 1 case, respectively. In either case, we go from an even number of photons down to an odd number of photons. If we just measure the parity of the number of photons inside the resonator, we can see that when a single photon leaves, it goes from even to odd in both the case of a logical 0 and a logical 1. And so we can detect when an error has happened without detecting which state we're actually in. Of course, there are limits to this code. So what happens if 2 photons leave at the same time? But before you do a parity measurement check, then we go from an even number of photons down to an even number of photons. And so that's an error that you can't recover from. And similar ideas true for if you have heating. So if you heat up, then that's another state that you can actually recover from. So this is the simplest binomial code. The binomial codes are actually a class of codes, so you can come up with more complicated binomial codes that are robust to, for example, 2 photon loss or single photon heating, and a whole class of errors. And they're actually quite related to the cat qubits that you may have seen earlier in this workshop. But I think it's really like the simplest code to understand out of all the bosonic codes. So that's where I like to start. But there are other kinds of bosonic qubits. So cat qubits are one example of a bosonic qubit. This two-legged cat, two-component cat qubit is not an error-correctable qubit, but it is a biased qubit. So as you increase the number of photons in this cat qubit, you can, depending on what axes you choose, like this is a choice, you can exponentially suppress bit flips while only linearly increasing phase flips. That's really interesting because then you can imagine putting this together into repetition code where you use that repetition code to correct for the remaining phase flip errors. So this cat repetition code is quite an interesting idea. There are companies out there that are, for example, Alice and Bob, that are looking at putting cat qubits into other kinds of LDPC codes. So something maybe not as symmetric as a surface code, but some LDPC code that can help correct the remaining enhanced bit flip errors and perhaps even the remaining bit flips or suppressed bit flip errors. That's an example of how you can layer, bosonic qubits with other kinds of codes to achieve maybe more hardware efficient logical qubits overall. The kinds of qubits that I'm interested in my research are called GKP code qubits. These Gutsman, Kitaev, Preskill code qubits. This GKP code actually was first theoretically formulated in 2001. And we'll talk about the details of the GKP code, but it was almost 2 decades later, maybe 1.5 decades, almost 2 decades later, that they're actually implemented in an experiment. So it took a little bit of time for us experimentalists to catch up to this very cool theory. But these codes are quite nice in that, in some limit, they are the most robust codes against certain kinds of error channels. For example, photon loss, which is a dominant loss mechanism in these resonators, in these quantum harmonic oscillators. And as we'll later see, these GKP code qubits can actually handle a wide variety of loss mechanisms. So it's quite a nice and robust code. And so that's what I'm most interested in. So let's get into what a GKP code actually is. To do so, we're going to start with the ideal GKP code. The ideal GKP code states the logical 0 and the logical 1. They're not as nice to write down as the binomial code, but the way to think about them is that they're some interesting superposition of infinitely squeezed states. This is the ideal code. They're infinitely squeezed states of, for example, a particular position or a particular momentum. So here I'm just plotting the probabilities versus momentum, the probability versus position for the plus state in this like faded out red, and for the minus z state, the 1 state, the plus z being 0 and the minus z being 1. And you can see these like infinitely squeezed, like infinitely precise position states over here and momentum states over here. And that's not really physical. That requires infinite energy, but it is a good place to start. So grid states, I think the best way to kind of understand them is by looking at their logical operators. So looking at the logical x and the logical z operators. And the logical z operator is really just a displacement in the y axis over here, momentum, by L/2, where L is the spacing between these two dark arrows. And so the logical 0 state and the logical 1 state are essentially just shifted versions of each other, shifted by L/2. And so let's look at what happens when there are errors in the system. When there are errors in the system, for example, you can think of noise coming down a drive line. I'm not sure how deep you got into the Hamiltonians of these superconducting circuit systems, but that might look like this drive term might look like this A plus A dagger term, right? And if you have some noise on that drive, that looks like some noise on that looks like a small displacement error. So this grid is displaced by like a small amount. And if we're within this green arrow over here that I've drawn, we can actually take this small displacement. We can map it onto a control qubit using something called a conditional displacement. This is basically a displacement on the resonator conditioned on the state of the qubit. So displacements are basically moving this grid around, in this phase space. And a conditional displacement is, for example, moving to the right if the control qubit is in the ground state, and moving to the left if the control qubit is in the excited state. And just to make sure that we're all on the same page, the information is still being stored in this resonator. The control qubit, even though we're calling it a qubit, is really just a control circuit used to control this resonator. So in the same way that you can displace the resonator condition on the state of the qubit, you can actually pick up a phase on the qubit conditioned on how much the resonator has been displaced. So this small displacement can actually translate into a phase on this control qubit by doing this entangling gate, this conditional displacement gate between the resonator and the control qubit. And then by doing a single qubit rotation, you can map this you can do a single qubit rotation around the y-axis, map it so that when you measure the qubit, you can actually get information about the error that has occurred. And one thing that's really important to note is that regardless of if you were in logical 0 or logical 1, because what we're doing is we're measuring modulo L/2. Regardless if you're in logical 0 or logical 1, you would measure the same small displacement of this grid. And so this is another way in which we can detect that an error has happened without detecting which logical state we're in. And then you can actually, and we detect exactly what error has happened by mapping that error onto the control qubit and reading out that control qubit. And the final thing I'll say is that you can actually reset this control qubit. Instead of reading it out, you can actually reset it to get rid of that error. And the way I like to think about this is entropy or errors are kind of introducing some sort of randomness into the resonator. We're mapping that randomness onto the qubit, and then we're cooling that randomness out of the system. So this is called entropy dumping. We're taking the entropy that was in the resonator, putting it onto the qubit, and we're dumping it out by just resetting the qubit. So just resetting it back to the plus state. Instead of actually reading out the state of the qubit and doing something with it. So I think this is actually a really cool and key distinction between bosonic codes and the register-based codes. Most of the error correction protocols for these register-based codes, and I think there's like a few exceptions that are coming up very recently that I don't know much about personally, to be honest. But most of these register-based error correction codes use measurement to measure stabilizers and then decode those measured syndromes to figure out what errors happen. In bosonic codes, you can actually do this autonomously. You don't actually need to measure. And so practically what that means is you don't actually need a really good readout. You just need a good reset. And a good readout is hard to come by. So that's another kind of cool advantage of the bosonic codes, that you can do this in an open loop way where you don't actually need to do anything with the information you measure on the control qubit. Any questions before I move on?
Yeah, we have some questions I can ask. First question is that what methods are being planned to have long range interaction between superconducting qubits vertically?
Yeah, it's a good question. So that's more related to the register-based codes, and it's a question that well, I think actually it's quite important for many things. There's a lot of exciting research going on in this, even in my group, in the engineering quantum systems group, where people are exploring different ways in which to create these long range couplers. And kind of one fundamental issue here is that the longer, imagine you had like a resonator that was coupling 2 qubits, or like some device that was coupling 2 qubits. The longer you make it, generally, the lower the frequency gets. And so as the frequency gets lower, this device, it starts to be more like thermally populated, and bad things kind of happen. And so that's a problem that that we're trying to solve and other people are trying to solve in different ways. They create these long range couplers that, that are able to with which we're able to engineer high fidelity gates. Yeah, high fidelity 2-qubit gates.
Thank you for your answer. Another question is that what is the limit of number of qubits we can apply the binomial code for error correction?
So the binomial code itself is just encoding one logical qubit inside this resonator. So yeah, so it's one logical qubit for this resonator. I do think it's an interesting question of like, can we come up with codes that encode, for example, two logical qubits of information inside the resonator? And there's a really nice paper that recently came out from the Michel Devray group, where they encoded a QDIT, so not just like a two-level logical logical qubit, but like three-level and a four-level like qtrit and qcort. And in this experiment, they actually showed break-even error correction. That means like error correction that actually helps for the first time in any platform. So I thought it was quite cool. So it's an interesting question. Can we encode more information than just one logical qubit in these resonators? Yeah. Any other questions?
Yeah, thank you for your answer. Another question is how do bosonic codes offer a hardware efficient path towards error correction? Could you please elaborate?
Yeah, so the main idea is that um, instead of needing many physical qubits for one logical qubit, we just need one resonator and a control qubit. So just less hardware.
Okay, thank you. I can ask another questions, then you can continue after.
Okay.
What is the correlation between the measuring displacement and error correction in GTP pods?
So errors manifest as small displacements. So if you can measure these small displacements, you can measure the errors.
Thank you very much.
Cool.
You can continue.
Yeah, thanks for the questions. Okay, so like I said, there's a way to actually measure and actually dump out these errors in an autonomous way. So you don't even have to look at what that small displacement is if you can just kind of dump it out. And there's this nice protocol that was constructed to perform this error correction for the finite energy GKP codes. So everything that I've been talking about so far are these infinite energy GKP codes that aren't actually physical, that require an infinite amount of energy. It turns out that you can slightly modify these to make them something you can actually implement in an experiment. And so the circuit that I was showing before was this conditional displacement with the qubit rotation. So, the center conditional displacement and this qubit rotation. The rest of these gates are just to account for the finite energy nature of the GKP code, these epsilons. And the size of this epsilon determines like how much energy is kind of in the system. And so this is called the SBS quantum error correction protocol. And the way I like to think about it is that errors are entering our system with some rate. Quantum error correction in this form is really just cooling us back to the code space. So errors are kind of these like this randomness, this entropy, these like excitations. And quantum error correction is bringing us back to the code space. It's cooling us. And so what we want is for our quantum error correction rate to be greater than our error rate for us to be able to break even, to be able to deal with whatever errors are hurting our system. What I'm showing on the right is basically what happens if you start off your vacuum with nothing in it, in the vacuum state. And then you just start running these gates, basically. Over time, if you just keep running this over and over again, you'll actually be cooled into the code space of the GKP code. And what you'll be cold to is the maximally mixed state of your GKP code. So this is the mixed state of your logical 0 and your logical 1. 50-50 in logical 0 or logical 1. And so you can see, like, from vacuum, if you keep applying this, just by applying this, again, not doing anything with the measurements, just resetting the qubit after each application of this circuit, we're able to stabilize the GKP code. All right, so we've been talking a lot about how a control qubit is needed to control over the bosonic mode to implement error correction. And so this control qubit is actually quite important, the properties of this control qubit. And to date, all of the GKP experiments and many other bosonic code experiments have their logical lifetimes, the lifetimes of the logical qubits created, have actually been limited by the lifetime of the control qubit. So one way to think about this is, okay, you need this control qubit to be able to control this bosonic mode. The reason why is because if you didn't have a control qubit, you would have only linear terms. You would only have the quantum harmonic oscillator potential and then maybe some drives, which are also linear. So you need a little bit of nonlinearity to be able to do interesting things. And that nonlinearity is a two-level system, typically. That's what people choose. And typically, it's actually a transmon controlled qubit. The T1s of these transmon controlled qubits, they're getting better day by day, but they're still on the order of 100 microseconds, 200 microseconds, on that order. And what we're seeing in all these experiments is that the lifetime of the transmon will actually determine the limit on the logical lifetime of the bosonic qubit. And so the control qubit bit flip errors are limiting the performance of these bosonic codes. They're the most limiting thing. And the interaction between a bosonic mode and the control qubit typically looks like some operator of the resonator times the sigma z of the control qubit. And so this sort of interaction term, it commutes with sigma z, because there's a sigma z here, and so it commutes with the qubit sigma z. And so at a high level, this motivates why bosonic modes are only weakly sensitive to control qubit phase flip errors, but the sigma x does not commute, and so they're highly sensitive to control qubit bit flip errors. Another way to say this is that the phase flip errors, they don't really accumulate, but the bit flip errors do. So as you have more and more bit flips on your control qubit, it keeps hurting, and it keeps hurting the information inside your bosonic mode. It keeps getting worse. And so to improve the performance of bosonic codes, we need a more bit flip protected control qubit. Our approach is to use heavy fluxonium. Heavy fluxonium is a qubit that has T1s on the order of a millisecond or more. And it's a different kind of qubit than the transmon qubit. It has this sort of double well potential where the G and E states are the ground states of these two wells. And so they're very well isolated, especially if you operate off of half flux, which is where we operate, off of like a sweet spot, because we want our T1 to be really good. We don't care as much about our phase flip. And just to kind of give you an experimental data point, there's a paper, break-even error correction paper from, again, the DevRay group, that in which the bosonic qubit was 65 times more sensitive to bit flips than phase flips. So really, we do care more about these bit flips. A particular form of the interaction in our experiment is actually this conditional displacement interaction, which is a displacement on the resonator conditioned on the state of the qubit. So this A plus A dagger is displacement, and then the direction of that displacement is dependent on the state of the qubit because of the sigma z. The first approach we took to this fluxonium controlled qubit project was to use 3D superconducting cavities. That's kind of that's the industry standard, so to speak, for these kinds of codes. Because these superconducting cavities have very high Qs, they have very long, they have very high T1s. For the bosonic mode, they're very high T1s, and so that's quite nice. And so really what we did is we just took these fluxonium chips and we just stuck them into these 3D cavities. The reason why we had multiple cavities was initially for like a different reason, and then we were able to use both of these holes to characterize two fluxonium chips at the same time. But really, what you should be looking at is, we have these three holes, one hole here, one hole here, and one hole here. The middle is storing the logical information. It's our storage mode. The one on the right is a readout resonator. And so let's just focus on the middle and the rightmost holes. So again, the middle is the one that's storing the information. The right is a readout resonator, and between them is a heavy fluxonium. And that's the first approach we took. It turns out, we ran into some difficulties getting flux into superconducting cavity without introducing too much loss. And that's in general a pretty difficult problem in the field. But it is a problem that some people have come up with solutions for, albeit a little bit complicated. And so rather than kind of implement these more complicated solutions to progress in this project, we decided to actually switch to what was our end goal already, which is to go fully to 2D. These cavities are really nice, but they're also quite large. Like they fit in my hand, and that's for one logical qubit. So I can't imagine, hundreds of these inside a fridge. And so the goal really from the get-go was to go to a fully 2D architecture. But on-chip resonators are, while being more extensible and scalable, are more lossy. And so to move to 2D, we must engineer a much faster quantum error correction rate than in 3D to deal with this increased loss. So photons are leaving faster in these 2D resonators, and we must be able to do error correction faster to deal with that increased loss rate. And to be able to do that, we introduced this sort of novel architecture where we're using asymmetrically threaded squid coupler, which has been used in other experiments, for example, with cat qubits. And we're using this coupler to couple our heavy fluxonium control qubit to our storage resonator. So we're actually able to increase our error correction rate by, in particular, speeding up the rate of conditional displacement gates. If you remember from that circuit, the error correction circuit that I was showing, there were a lot of conditional displacements, and it turns out those conditional displacements are actually one of the most time-intensive parts of that protocol. And using this coupler, we can actually make those conditional displacement gates much faster. And there are other benefits actually to using this coupler as well that we'll get into later in the talk. There's a little bit of kind of a novel treatment of these kinds of systems that we developed for this project, where we extended black box quantization, which typically is used for weakly nonlinear systems. For example, like a resonator coupled to a transmon. You'll black box quantization approach. You'll typically treat the transmon's nonlinearity perturbatively and then truncate it and use only some of that nonlinearity. You can't do the same thing in heavy fluxonium in terms of truncating nonlinearity because it's like very nonlinear, not just slightly nonlinear like a trans. And so, but what you can do is you can still use this sort of normal mode approach where you take the linear part of each of these circuits, use that to come up with the normal modes of each of these circuits. Looking at the linear parts of each of these circuits and also the couplings between them. Coming up with the normal modes, and then using that as the basis to write down the rest of the nonlinearities. This is something people typically don't do because they don't apply this sort of normal mode approach to very nonlinear systems like fluxonium. So I think it's cool to talk about this a little bit. And it turns out that this is something that is valid to do as long as we don't truncate that nonlinearity, as long as we treat that nonlinearity exactly. And when we do, we can actually make our calculations a lot simpler and also build some intuition. For example, the way to actually do a conditional displacement gate is to activate like a cross resonance style gate where we pump this coupler at the frequency of our storage resonator. And in doing so, this first term over here is the nonlinearity of the ATS. This second term is the nonlinearity of the heavy fluxonium. And so if we pump this epsilon of t at the storage resonator frequency, if we turn on this flux pump, then what will happen is we will actually, if you go through some math, we'll be left with exactly the term that we want, a conditional displacement term, a term which looks like a displacement on the resonator conditioned on the state of the qubit. And when this pump is off, when epsilon is zero, you can see that sine of zero is zero. And so the nonlinearity disappears from this coupler, and this resonator and heavy fluxonium are very weakly coupled. The other thing I'll say is that these metrics, for example, the conditional displacement rate, the rate of this conditional displacement, can be calculated with mostly analytic formulas with only some few inexpensive numerics, like looking at fluxonium matrix elements, as opposed to diagonalizing the whole system, looking at matrix elements of the whole system. I know that's a lot. I think that gets into like a very, that goes into a little too deep. And so if you want to take anything away from this slide, it's that by using this coupler, we can turn off the coupling between the resonator and the fluxonium. And when we want to turn it back on, we can just pump this coupler and we can turn on that coupling and get a conditional displacement rate that is proportional to the pump strength. And for reasonable pump strengths, we see that in simulation at least, we can engineer 8 times faster conditional displacement rates than what people have been able to achieve in past work. So again, by using this coupler, we can do conditional displacements much faster, which are a really important gate and the most time-intensive gate in our error correction protocol. So we can speed up our error correction by using this coupler. And when we turn off the pump, then our resonator and our fluxonium are effectively decoupled. And so chi, the dispersive shift between the fluxonium and the resonator, the kind of measure of how coupled they are, is quite small. And other things like Kerr, which is basically the idea that, okay, if you're using a nonlinear system to control a resonator, the resonator inherits a little bit of that nonlinearity, which you don't want. But the rate, the metric by which it inherits that nonlinearity is Kerr, and that Kerr is very, very small. It's about 100 times smaller in simulation than what people have been able to achieve in previous work. So this is quite exciting, just to motivate this platform. This slide is, I'll skip this. This is basically just motivating why it's good to have the ability to turn off the coupling. But really, you can just think of that as sometimes when you're not doing entangling gates between the resonator and the qubit, it's really good to decouple them because your qubit has noise and you don't want that noise to propagate into the resonator. Also, this is the actual device that we fabricated. It's unlike those big 3D resonators, 3D cavities. This is a fully on-chip 2D design where instead of the 3D cavity, we have this 2D resonator. And that fits, it's a 5 by 5 millimeter chip that fits in this package and then is mounted onto the fridge. And just some preliminary experimental progress. We measured, for example, the lifetimes of these resonators, and they're definitely not as high as the 3D resonators, but they should be high enough for us to do error correction, which is cool to see. We measured, these are some example data points for our fluxonium, and we're seeing above 1 millisecond lifetimes for that fluxonium within a wide flux range in which we want to operate, which is cool. So our fluxonium has, this millisecond T1 lifetime, which motivated the whole project, and the storage lifetime is also workable. Right now, what we're working on is really getting this conditional displacement gate up and running in our experiment with the coupler, and so that's still a work in progress. But to look at it at a high level, really the whole point of this new architecture is one, so that we can go to 2D, and two, because things are lossier in 2D, we want to be able to do error correction faster. And so compared to what people were able to achieve in past, like very nice experiments, where we're looking at about 3.9 microseconds, almost 4 microseconds, in terms of a single round of this circuit. With our protocol, we believe we can get about 8 times faster to deal with the increased loss rates in our systems. And these are just some simulations showing that given the speed of our error correction, given the lifetime we are seeing in our systems, we think we're well positioned to do break-even error correction, where our break-even factor would, and this is in simulation, of course, and things are different in experiment, but it's about 10 times whatever the best physical qubit is in the system. And for context, I think the best gain factors are still on the order of like 2 or 3 factors. So this would be quite a large gain factor. And then, of course, the absolute value of the logical lifetime is also important. And that's something that I think will increase as we, for example, make better 2D resonators. So I think just doing break-even error correction would be very cool in this system. I just want to talk about all these awesome people that make this kind of research possible, all the people in my group, as well as in MIT Lincoln Lab, with whom we collaborate, where we get our chips fabricated. And then finally, I just want to give a little bit of a teaser for tomorrow, where we'll talk more about software. One thing that has been quite useful in this project is this set of tools that we developed, simulation tools that are auto-differentiable and accelerated using JAX. They're all built on Google's JAX framework. If you heard of TensorFlow, this is similar to that, slightly different, but it's similar in that it allows you to accelerate your code on GPUs and TPUs in a very easy way. And it's also auto-differentiable, meaning that you can, if you write functions using JAX, then you can take a derivative of the output of any function with respect to the input of any with respect to any input of that function, which can be quite a powerful tool. So JAX Quantum is like QTIP, but with JAX. So you even import JAX Quantum as JQT, and then you can use it in the same way. QCSys is like SC qubits, but with JAX, it's nice to construct superconducting circuit systems, optimize them. There's also treatment. We have a built-in treatment with flow K-theory. So if you want to treat periodic drives with flow K-theory, that's built in there, and some other cool features. And bosonic, which is kind of like Qiskit, but for bosonic qubits, where you can basically create these different kinds of circuits built of like cat codes, random wood codes, GKP codes, and a whole zoo of bosonic codes, and do gates on them and between them. And bosonic, for example, has JAX Quantum as one of its dependencies, and QCSys. And so all these packages work really well together. You can also use them separately. They're all open source. You can pip install them. I would actually recommend just going to their repos and installing from source, because we're updating them like very frequently. So PyPy might not have the most up-to-date version. But we'll talk more about these tomorrow. And you can actually run simulations like the one that I was showing over here using something like bosonic. Yeah. And really quickly before we end, I want to just plug one thing. We always have a hackathon every year in January at MIT. We see representation from many different countries, like almost 80 countries. Many people come in person or attend remotely. I had the pleasure of chairing this event in 2023, and there's another like very talented team chairing it this year. So you can go to iquac.mit.edu and sign up there. Now in the remaining few minutes, I'm happy to take more questions. I know we took some questions along the way as well, but I'm happy to take some more questions. Yeah, thank you.
Thank you very much for an interesting lecture. Now we have a few questions. The first question is, could you see a similar design to be released based on another pair of non-commuting variables? like charge and flux instead of position and momentum. Something similar only with transmons or fluxonium or any other superconducting qubit instead of bosonic oscillators.
I don't think I understood the question.
I can repeat it.
So yeah, could you repeat it, please?
Could you see a similar design to be released based on another pair of non-committing variables like charge and flux instead of position and momentum? Something similar only with transmons or fluxonium or any other superconducting qubit
Okay.
instead of bosonic oscillators.
Yeah. To be very clear, what I'm calling position and momentum are very similar, the same thing really as like uh, the charge and flux. So people kind of use these interchangeably. You'll like call, for example, your charge, your position, or your momentum. It's up to you. It's a choice. And the flux, the conjugate variable. Um, so to be very clear, these like this resonator or even 3D resonator, really you can just think of that as an inductor and a capacitor, right? So you use the same techniques of like um, circuit quantization, whatever, to understand these quantum harmonic oscillators. It's an interesting question about like, can we implement bosonic modes in other circuits? Is it um, really we want these circuits to be as linear as possible, so you really do just want a capacitance and inductance. But there's some interesting ways to get these inductances and capacitances. There's some people in our group, for example, that work on kinetic inductances, materials that have like high um, kinetic inductance that allows us to create like much smaller 2D resonators. Yeah.
Okay, thank you for your answer. Another question is which approach we can use to activate a some flux drive?
Um, yeah. So uh, the way this sum flux drive works, I didn't really talk about it that much. Um, is this is you just have a flux line that's going up to this. Actually, the yeah, you can see there are these two flux lines that are going up, and this is really just copied from another paper, I think Bordeaux et al. 2022 or something like that, where you have these two flux lines, and there's a current that's going um, through the structure. And by changing the kind of phase on these lines with respect to like the relative phase, we can achieve both a common flux and a sum flux. I'm going through loops that are where my cursor is to get the same amount of flux through the ATS loops. Yeah.
Okay, thank you. Another question is why the lifetime of a 2D resonator is less than 3D resonator? How can we increase the lifetime of the 2D resonator?
It's a great question. Um, these 3D resonators, so generally surface interfaces are lossy. So whenever you have like an interface between like a superconducting metal and some other superconducting metal, or just like that and vacuum or air, different things like oxides, for example, can form. And if the mode participates in these um, surfaces, then the mode will be lossy by determined by like its participation in these different kind of surfaces. In 3D, you have a nice like volume to surface area scaling. Um, and also you're able to do things like etch these cavities and create structures where the mode is very far from, for example, lossy interfaces like the lid of this thing. We'll put usually a post at the bottom so that the mode is very confined down here and doesn't actually leak out through the top of the superconducting interface between like the lid and the structure. So you can do things like that to engineer really high Qs. In 2D resonators, um, there's a lot of surface area and um, there's some things you can do. So one thing that we did is we increased the gap, the coupling waveguide gap, so as to minimize participation in surface interfaces. It's not a new idea, but it's something that we used in our experiment. Um, and other people in our group are working on, for example, capping this aluminum with other kinds of metal that don't form oxides that are as bad. So there's definitely a lot of exciting work going on in these 2D resonators to make them better.
Professor Shantanu, thank you very much for this interesting lecture and for your time and answer all questions. Thank you very much.
Bye-bye, everyone.
Bye. Okay, everyone, we are continuing with another lecture. Now we will be with Professor Arjana Kamal. Professor Arjana Kamal had her bachelor degree at St. Stephen College in Delhi, India, and had her master degree in Indian Institute of Technology in Delhi before she moved to Yale University to continue her study in quantum physics and quantum information for her PhD. She then moved to MIT for her postdoctoral work before joining UMass and then worked as associate professor and a PI at Quest Group and currently working at Northwestern University in the Department of Physics and Astronomy. She received the Teaching Excellence Award at UMass in 2020, and in 2021, she was awarded the AFOSR Young Investigator Award as well as NSF Career Award. And today she will present the lecture non-QMD, non-Markov effect in qubit. Professor Arjana Kamal, welcome, and thank you very much for accepting our invitation.
Hi, can you hear me?
Yeah.
Hi, I'm not sure why I'm not able to turn on my video. It just says it's unable to detect the cameras, but I guess as long as you can hear me, it's all right.
Yeah.
That's okay. Let me try to share my slides. Those are much more important. Anyway,
Okay.
thanks. Very nice introduction and the invitation to speak. Let me see if I can share my slides. Can you see my slides?
Yeah.
Is this okay?
Yeah, that is okay.
You can see this display, right? Like not the actual presentation, not the presenter's view. Is that right?
Yeah, it is non-grounded and non-Markov effective circuit presentation. Yeah.
Okay, great. Thanks so much. As I said earlier, thanks again I'm very excited to present our work over the past few years, where we have actually discovered surprises in circuit QED, which is supposed to be, oh, I think it's showing the presenter mode. Let me see if I can. Let me see. Sorry, it was somehow showing the presenter mode from what I understand. Is this, are you still seeing the presenter?
Yeah, that's okay now.
Okay, great. Yeah, thanks. So, okay, great, thanks. Yeah, so these are the things which we have actually discovered as actually surprises because it's a very well understood system. It is now the leading platform for several industrial and academic applications. By the way, I have planned a speaking time for 40-45 minutes, so please feel free to interrupt. I probably cannot see the chat window, but just maybe the host can just let me know if there are questions in the chat. So before I start, I would like to thank all the collaborators and the people who actually do the heavy lifting and all the work actually. The postdocs and graduate students. This work started actually with our alums, Jihav and Juzar, who were postdocs, and now they have moved on to their next phases of career. And now it has been taken forward by several graduate students. And also we are, for this particular experimental results, which I'll actually show you, we actually collaborated with IBM Quantum. So in that sense, it's most appropriate because it's an IBM Fall Fest. So without further ado, let me just flash this slide, which is actually the rite of passage for any circuit QED talk. Everyone is aware that this is basically it started out as a strong light matter interaction platform. When we say strong light matter interactions, we essentially mean that the coupling between the light and matter in this case is some kind of microwaves, and the matter is qubits, superconducting qubits. The coupling between them overwhelms any kind of decay channel on the system. That's the sense of strong coupling circuit QED. And this kind of regime is essential to achieve any kind of coherent control or quantum information processing. This breakthrough was achieved almost 20 years ago, and we actually had a circuit QED at 20 celebration this year in January. So the field has come a long way since then. But in terms of the typical parameters which everyone uses, these are the things which we typically do. We have both the light and matter, which is qubit, and the resonators. This is a pictorial representation. This is a purest representation with ball and stick diagrams. They are both few gigahertz. The coupling is of the order of 100 megahertz, and the rates are of the order of 0.1 to 1 megahertz. And now with 3D architectures and noise protected qubit designs, these are down to even 0.01. Like you can add more zeros after the decibel now. So things are looking really good in terms of coherent physics of these systems. They are extremely scalable, very easy to scale up. And in the circuit QED regime itself, there are two kinds of regime. One is the resonant circuit QED, and another is the dispersive circuit QED. So what do we mean by resonant and dispersive circuit QED? So the resonant circuit QED is the regime which is what we explore in quantum control, which is basically that you have quantum gates, you're driving things on resonance, you're trying to prepare some state, you're trying to perform some quantum algorithm. And here, when you drive the things through the cavity, the one way of thinking about resonant circuit QED is that your G, or the coupling, actually is much bigger than the detuning between your system and whatever the ancilla system is, in this case, the cavity. So this is the regime of resonant circuit QED. It is now even being adopted in parametric platforms, where you can actually just pull excitations out of the qubit, put them in the cavity, do some kind of active resets, or some kind of interesting measurement physics. The other regime is the dispersive circuit QED, and this is the regime which you might have heard when people think about reading out qubits. Reading out means that you are not actually trying to control the qubit or change its state beyond what is absolutely necessary measurement back action. And for this kind of circuit QED, you do not actually want to pull excitations into or out of the qubit. That is the reason that the coupling is actually deliberately considered much smaller than the detuning. So the processes are so off resonant in this regime that in some sense you are in the perturbation theory regime, and at best what you can do is to modify these energy levels of these qubits a little bit, and these energy levels can modify these energy levels which they are coupled to because of the hybridization. And we never look, and this is the sense of indirect measurement, whereby looking at the cavity frequency which gets shifted in response to the qubit, you basically say, okay, I can infer whether the qubit is sitting in its ground state or excited state. So this is a very standard paradigm of quantum the qubit readout. And let me say a bit more of why let's focus on this dispersive circuit QED regime. So as I already said, this dispersive circuit QED is when your detuning between the qubit and the resonators is much greater than the coupling between them. And in this kind of perturbative regime, you have this very nice looking Hamiltonian to at least order G square. So you can actually do a perturbation series. And this perturbation series can be done directly on the Hamiltonian operator, which is called typically sometimes called dispersive approximation or Schiffer-Wolf transformations. And you can write this new Hamiltonian, which is diagonal in both the qubit as well as the oscillator. So for example, you have some kind of a photon number term, you have some qubit frequency, and then you actually have some shift on the qubit, which is typically sometimes called the Lamb shift. It's just this is a borrowing from the AMO literature, that when you actually couple the qubit to the cavity, even if the cavity is completely unexcited, which means B dagger B is 0, still it has vacuum fluctuations in its ground state. And that vacuum fluctuations is enough to give you a shift to the qubit, because quantum vacuum is not empty. So any kind of ground state quantum vacuum induced shifts are called lamp shifts in AMO literature, and we just borrow that terminology in circuit QED. And this is the most important term. This is the term which is the interaction term between the qubit and the cavity, which, as you can see, commutes with both the qubit and the cavity Hamiltonian. So this is quite nice, because when you have an interaction which commutes with both the system and the meter, this was actually originally thought in the context of gravitational wave detection, because when you are trying to measure very, very small displacements on very, very large objects, you cannot afford too much noise because of non-commuting quantum measurements. So the idea that your quantum measurement Hamiltonian commutes with your system is the concept of quantum non-demolition, that the measurement back action is not there. Which essentially means, for example, let's say if you are measuring a value, if you have a measurement Hamiltonian, which is, let's say, you're measuring the displacement operator, this will not commute with the B dagger B, because it's B plus B dagger. And because of that, the several future measurements are spoiled, because the measurement itself induces a back action on the future measurements of what is being measured. So this kind of quantum non-demolition interaction is absolutely essential for error correction and this kind of physics, so that there is no measurement back action. And that is why we all love this Hamiltonian so much. Now, you would think that I just told you that this is a measurement doesn't destroy your qubit. And now this was the puzzle which has been annoying circuit QED experimentalists and theorists for quite some time. That this is sometimes called T1 anomaly within the inner circles of circuit QED. That even when you are comfortably in the dispersive regime, which means when G is comfortably in the regime when you can do is small enough as compared to the detuning that you can do this transformation, still the fact that you are reading out can change the dynamics of the qubit, and that should not happen. So this is actually the data which was taken by IBM experimentalists on their Sherbrooke quantum processor, where they are to show what they were doing is it's a very simple experiment. They actually do a pi pulse on the qubit. So they excite the qubit and then they wait and then they start measuring. And of course, that is our typical T1 measurement, except they have two versions of this experiment. In the red experiment, they do not put this pulse on the cavity. So they are just driving the cavity when the qubit is being measured, or not. So when it is the red data points, they actually do not have this measurement pulse on the cavity, and they measure a T1 of 270 microseconds. And when they put photons in the qubit, they actually find a reduction of T1 to 70 microseconds. So it's a huge depression of qubit coherence, even though you are not driving the qubit. And this is happening even when there is no direct control line on the qubit, and it is interacting only dispersively with the cavity. So this is the meaning of T1 anomaly, that the fact that you have any kind of photons in your readout resonator can destroy your qubit. Even whether you collect the photons or not, it's immaterial. Even though you have this seemingly commuting interactions. Now, similarly, this is another manifestation of this effect is that this is a data from ETH group from Andreas Walraff, where they were trying to measure, basically trying to characterize their readout error as a function of number of photons in the cavity. So of course, and these are the intentional photons, the measured photons. So now the point is, if you drive the cavity hard, you will, of course, expect to see that you are extracting information at a faster rate. So you expect your error to go down. This is what you expect from the theory point of view. But they found that as for fairly low photon numbers, like 2 or 2.5 or 3 on average, these are average photon numbers, they actually find that the error starts increasing instead of going down. So you are actually trying to put more photons to extract information at a faster rate and actually achieve a higher readout fidelity, but actually it is getting worse. So there's this upturn in the readout error, which is very surprising. And this is the work which is almost like more than 10 years ago at Berkeley from Irfan Siddiqui's group, where basically they showed that the cavity photon occupation number, as they increase it, they actually find spurious qubit excitation. Again, this is very far off resonant regime. These photons have nothing to do in terms of matching their frequency to this omega s. This is very different frequency from this, but still they manage to see a lot of excitation in the qubit just because they're putting photons in the cavity, which are very off resonant. So all these things have been like basically indicated that something is not really complete about the picture we have of this dispersive regime, where we think that the qubit should remain like it should not lead to any excitation in or out of the qubit, as I explained earlier, because you're in a far off resonant regime, and therefore you should never have uh, any kind of demolition or excitation of qubit population. But people have observed this. So there have been several attempts, starting, I would say, with Alexandre Blaise group in in late 2010s, and so it has been kind of a 15-year effort where people have thought about dress dephasing. That maybe there's noise at the detuning, which is getting some kind of a up converted or down converted, and that is leading to this physics which we have missed. Then maybe the cavity inherits some kind of non-linearity from the qubit, and maybe these non-linearities are enhanced, and then they have a back action, because who knows what happens when they are high order non-linearities. And then Google group has been talking about what they have started calling MIST, or measurement induced state transitions, where basically the idea is that maybe the cavity is not affecting the lower levels of the qubit, but cavity is hybridizing with the higher levels of the qubit, because no qubit is actually a two-level system. Everything has higher levels. And maybe because of this hybridization of the higher levels and some kind of non-zero matrix element between those higher levels and lower levels, some T1 process is happening, which we didn't account for. So as you can see, it's a pretty interesting multi-level, non-linear, out of equilibrium problem, and people have come at it from various types. And then, of course, people have also thought about, okay, maybe we just don't know how to measure correctly. Maybe we just the amplifier, like I don't know if I think the previous talk might have shown you this, but sometimes we in the measurement chain, there can be a pre-amplifier just after the readout, and that might be leading to some kind of back action. So it is some kind of, so the noise is actually amplified and not really the quantum noise you think it is. But the problem is that there have been experiments where you can mitigate these effects. Basically, what I mean is, yes, all these things definitely can lead to a problem with T1s. However, there are experiments where, at least if not one by one, you can actually, if not all of them, but one by one, you can actually remove these effects. For example, even when you do not drive the qubit, so this is not like some kind of driving enhanced nonlinearities on the qubit, then also you see a T1 demolition with readout. Similarly, there are these other very weird things which happen. I'm sure an experimentalist can share their frustrations about this. You measure a T1, let's say you measure some values, and then you go and have a cup of coffee and you come back, and it's possible, not always, but it is possible that you will suddenly measure a T1 which is 2 times lower. Nothing has changed. So there are actually temporal fluctuations which we don't understand. And this is also a part of some non-equilibrium physics related to this dispersive regime, which we are not fully getting. And this is not some quasi-particle problem, like some random quasi-particle hitting you. And then even more mysterious, the plot thickens here, because some studies have actually, like several studies have described the demolition that T1 reduces when you're reading out. But some studies have also showed that sometimes T1 gets better. That's really surprising, that you actually, it's not even always the same effect, even qualitatively. So then we actually kind of stumbled or accidentally stumbled into this problem. And we said, okay, let's try to actually solve this problem. And our guiding principles were, let us try to come up with something which is not system specific. People have seen these effects from, transmon to fluxonium to several superconducting qubits. So we should come up with something which is not model specific, because this seems like a very fundamental quantum open system effect. And then hopefully we should also, the other guiding principle was Occam's razor. And when I say Occam's razor, what that means is that whenever you are faced with two equally good hypotheses, you should always choose the simpler one. The power of theory is in its elegance and simplicity. So hopefully we will not need to introduce too many unknowns or too many effects to capture this effect, which everyone seems to be seeing and no one understands it. So our first clue was the following, which came from also IBM data. So I just showed you this dispersive Hamiltonian, right? This is the interaction which is commuting. And now what IBM did was they actually used in some sense an ancilla qubit to measure the density of states of their environment. So T1 is happening because of something coupling to the qubit, and they wanted to map their environment. So there's very nice paper by Rob Schwelkoff and co-workers which is called qubits, literally called qubits as spectrometers of noise. The idea is that if you measure the rate of the qubit, in some ways you know what's your environment, because the environmental spectrum, like whatever noise or crap you have in the environment, that sets your T1. So in some sense, if you measure the T1 of your qubit, it gives you a kind of a picture or a glimpse of what your environment spectral density looks like. So that is what this is showing. They actually took an ancilla qubit and they measured its T1, and this had some structure as a function of detuning. So this was a tunable qubit. So they were just basically sampling what kind of frequency spectrum the environment has. So based on the measurement of a frequency dependent T1 measurement, you can infer what the frequency or spectrum of your environment is. Now, if you have seen Fermi's golden rule, what does the Fermi's golden rule say? Fermi's golden rule says that the decay rate of now the intentional qubit which you want to measure should basically be equal to some kind of environmental noise times some matrix element of how. So it's basically means that your decay rate is set by how much crap there is and how strongly you couple to that crap. So if your matrix element is very large, that means you're strongly very coupling to the noise. So then your T1 will be worse. Or if you have too much noise, then also your T1 will be worse. So basically, if you just use this Fermi's golden logic, and then I say this basically, if I put more and more photons in the cavity, what will happen? The B dagger B will affect, like, in some sense, change the frequency of the qubit. And then let's say in this particular physics, the transmon chi is always negative. So the more photons I will put in the cavity, the more stark shift I will dial on the qubit. So essentially what will happen is that if I'm trying to basically, I don't know why that did not work, but if I'm trying to scan this particular thing from here to here, I should expect a T1 profile, which is almost like a mirror image, inverted mirror image of this environment, correct? Because basically when I have no photons in the cavity, I'm somewhere here. Then I put some photons in the cavity, it shifts my qubit frequency. So then I sample this peak. So my T1 dips. Then I go further. Then I'm here. Then the T1 improves. And then I again sample this peak. Then my T1 dips again. And then finally it improves. So basically T1 should follow according to this dispersive Hamiltonian. That's what it should look like. However, what IBM measured was almost like a smooth envelope. As a function of photons, they were not seeing any peaks and dips, even though these both are IBM measurements. So that was the first clue that this picture is not working. This doesn't make sense. The more you stare at this data, the less it makes sense. Because according to this, the only thing the photon should do in the cavity is to just move where my qubit frequency is and change the spectral density I'm seeing. But that's clearly what's not happening. It almost looks like a smooth envelope. So that was our first clue that there's some kind of an averaging effect going on. So how do we capture this averaging? And that's where we started thinking about, yeah, people think about this off-resonant and resonant regime in the context of Hamiltonians, but we should be thinking about in terms of dissipation also. So now what the only change here is I have put a kappa on the cavity, this gamma B, which is the decay line width of the cavity. And now if I ask you now, what is resonant and dispersive when the system is actually an open system? That's the meaning of an open system, right? It decoheres. Here, what you can do is you can say, oh yeah, from the point of view of a qubit decoherence, what I should do is I should trace out this cavity and it should find an induced decay rate and an induced frequency shift on the qubit. And now you can again describe your resonant and dispersive regime from the point of view of these rates. So this is the intrinsic rate of the qubit, which is gamma s, which is not because of the cavity. And this is some kind of a Purcell decay rate, which is through the cavity. That's only happening because cavity was coupled to the qubit. So the resonant regime is when this kind of the detuning between the qubit and the cavity is less than its the cavity line width. And this is the kind of regime which you see in optomechanics. For example, when you're trying to take excitations from the qubit and put them in the cavity to cool the qubit to its quantum ground state, that's what you will call resonant. And the dispersive regime is where you get Purcell formula. So this is the very famous single mode Purcell formula, which is just saying, yes, there is some decay on the cavity that couples to the qubit, and that means that now the qubit can decay to the cavity. So the qubit T1 actually is this formula. So now all this works, but you can see both these formulas do not know about gamma S. Gamma S is the intrinsic decay of the cavity. And you should be saying, okay, but that's fine because gamma S is qubits doing its own thing. And I am interested in what cavity makes it do. So maybe why should I care about gamma S? And that was the breakthrough which we actually found, that actually it does matter to gamma S, the orange guy, what the blue guy is doing. So in presence of multiple decoherence channels, you cannot ignore the other. That is the punchline. If there's one punchline you want to take from this section of the talk, you cannot ignore the previous channels of decoherence when calculating new ones. There's an interplay of intrinsic and induced decoherence channels. So we have started calling this DISCO, which is basically an acronym. It stands for Dissipation Incorporated Self-Consistent Master Equations, which can describe decoherence on systems which know about their all other decoherence channels. So that's why the word self-consistent and dissipation incorporated. And it's specifically relevant to circuit QED type scenarios where ancilla systems, whether be it like your ancillas in error correction protocols or cavities because of readout, can lead to a very strong dissipation on the system. Then this kind of interference effect, we always think of interference effects only in the context of Hamiltonian, but even at the level of dissipation, these interference effects can be important. And this is a bit of a technical one, so I'll skip, but we actually find that with the maths allows us to write what are called completely positive phase preserving forms, or CPTP forms, which are Lindblad type equations, while incorporating all decay channels. I'm going to skip this in this interest of time. So coming back to the original readout problem, what was actually we were missing? So as I said earlier, the unitary picture of dispersive readout just says that if you have a qubit frequency here for 0 photons in the cavity, when you put some photons in the cavity, it shifts. But what we find is that actually, when you measure a quantum system, you also dephase it, right? That is a very well-known phenomena of what is called measurement-induced dephasing, which means that qubit line not only shifts, but it also broadens. It also becomes broader. It's not only shifting, but it's actually covering more spectral region. And now this kind of shifted and broadened line, that has to convolve with the kind of spectrum or the environment spectral density of states you have. So there can be two regions. One region, there can be two scenarios. One scenario can be that you were actually off resonant from some hotspot in your environment, and then your qubit shifted and broadened, and this broadened peak, it actually ended up coinciding with some peak of the environmental spectral density. That means that you will have anti-Zeno physics. Anti-Zeno means that it's almost like that you measured. Because of that, the qubit shifted and broadened, and now it experiences a faster than usual decay dynamics because of the measurement. The other scenario is that you originally qubit was sitting at some kind of a hotspot, and somehow because of the measurement induced dephasing, you actually now sample this less because it's now happens to on the tail of the broadened qubit line. And because of that, you are actually better protected than what you were just because of measurement. So in this picture, in some sense, this is the same idea of what you might have heard of xenophysics, that a watched pot never boils. This is what is happening here. But in quantum physics, it's not just Zeno which can happen, it's also anti-Zeno is allowed, that a watched pot can boil faster. And that is what is happening in this scenario. So that's why it's called, I'm calling them anti-Zeno and Zeno. And when we calculate these rates in our using the Disco master equation, we actually are able to explain an increase or decrease in qubit lifetime with cavity photon number. NB is the number of photons in the cavity. And again, as I said earlier, this is in deep dispersive regime. So in some sense, what we find is that T1 modification or this T1 anomaly due to readout, it's a very interesting idea. It's a very interesting thing. It's as if the qubit T1 is modified because of its own T2. And why is there this T2? This T2 is this broadened line width, which has happened because of measurement-induced dephasing. So it's almost like a T2 induces a T2 of the qubit, which it has developed due to measurement, induces T1 on the qubit. And that T1 can be either increasing or decreasing as a function of measurement strength. And then one can ask, well, but if you recall, I said, usually people see T1 gets worse. Sometimes it gets better. This formula or this formalism also explains that, because you can see T1 will improve when you actually have the blue physics, which is called the xenophysics. That only happens near resonance, that there is some kind of a resonance between the qubit and the environmental spectral density. So xenophysics is a very special resonant phenomena. So it happens less often. Most of the times you see anti-xeno. And this was actually an insight which was originally also given, not in this context of such strong coupling regimes, from Kaufman-Kurisky, who actually discovered the anti-xeno physics. Before that, people only thought about xenophysics. That actually anti-xeno is much more common than xeno, because xeno is a resonant phenomenon. So we actually recovered the Kaufman-Kurisky result in disco formalism. However, we are able to actually predict exactly what the IBM was seeing, whereas if you use their analysis of xenophysics, it actually doesn't do a quantitative agreement with the data because of strong coupling problems. So this was actually measured by IBMs using the IBM people at Yorktown Heights, using very intelligent experiment, I would say. What they did was they actually took a transmon, which was the data qubit, and they coupled a defect transmon, which is kind of an engineered TLS or two-level system with fairly strong coupling, actually. So they were in this so-called intermediate coupling regime of sorts. And now what they did was they basically said, okay, we will first prepare the qubit. There is some delay, and then you measure. And that is how you typically do the T1 measurement. However, they also had some kind of a flux noise on the qubit. This flux noise can lead to a broadening of the qubit irrespective of the cavity. So they were just trying to really confirm this idea that it's not the shift, but the broadening of the qubit line or its own T2, which can affect its T1. And then this defect qubit can also be put in resonance or not with your data qubit. So they had a full access control of both the detuning with from this defect qubit and also the dephasing, which they can act on the data qubit. And then they took this experiment, they basically measured T1 as a function of this induced dephasing and detuning with this Bath qubit. And you can see that when you are on resonance, you can actually find very large decay rate, but away from it, you can either be decreasing the rate or increasing the T1, or increasing the rate or decreasing the T1 as a measure, as a function of dephasing, which is the T2 of the qubit. And there's no free parameter in this theory. So we actually find a very good quantitative agreement. This is the disco prediction, which essentially proves that it's actually the T2 of the qubit, which affects its T1 because of interaction between different mechanisms, which usually we think are completely independent. So I'll actually stop here. This is the first part of my talk. Are there any questions? And then I think a few more slides on the non-Markovian aspect.
Yes, thank you very much for your presentation. We have two questions I can ask now. First question is, dispersive QED is reading out qubit. Then why we do the indirect readout?
I'm sorry. If I understand the question, you're saying in dispersive QED, how do we do the indirect readout, or?
Yes, why we do the indirect readout?
Oh yeah, okay, I see. Yeah, so the point is because you don't actually want to. So this is a it's a very good question. We actually always want to make indirect measurements on quantum systems for the simple reason that you actually want to not actually couple the qubits directly uh, to your measurement apparatus, in some sense, your measurement lines. So what we typically do in quantum systems is to try to first couple them to some system and then look at the system they are coupled to, and that is a sense of indirect measurement. This kinds of measurement can be shown to be completely QND. Because think about it, like if you have a qubit, what will you measure? You'll measure sigma x or sigma z or something. And that means that you will not be able to measure that same quadrature again and again, besides the fact, because of the non-commuting nature of these operations, and besides the fact that these measurements would be destructive. Destructive means you will actually end up actually extracting information out from the qubit. The only way you know that the qubit is excited is by actually trying to collect the photon and de-exciting the qubit. And that's not what this kind of readout does. It only tries to say, oh, if the qubit was in the excited state, I would have seen this frequency. If the qubit was in the ground state, I would have seen this frequency of the cavity. So in that sense, the QND readout are non-destructive because they're not actually extracting actual information or energy from the quantum system they're trying to measure.
Okay, thank you very much for your answer. Another question is, are two-level system the dominant source of superior excitation in superconducting quantum circuits? I recall seeing a similar graph in another presentation about two-level system.
Very good question. So two-level systems are these kind of funky spectrum which you are seeing. This is not designed by IBM. This is what they ended up measuring. So all these peaks, they think it is some kind of a TLS. So yes, I think two-level systems are still, I would say, one of the leading candidates of limiting qubit performance. It is now happens that there can be certain qubits which can be, as I said, what you can do is, this is something which is just there on your chip, but you can make the coupling or the matrix element with which you couple to these things smaller or larger by clever qubit design. And that is what a lot of these noise protected qubits, or even maybe that was actually one of the original motivations of fluxonium, they do. They basically try to reduce the matrix element. So given the same amount of noise, you will still end up having a better T1 because your matrix element will be smaller. So same number of TO2, TLSs and everything. Yeah.
Thank you very much for your answer. I think we have no more questions, so you can continue.
Thanks. So I'll go forward and I'll go further towards the next part of my talk, which is a little bit of shifting gears about the non-Markovian aspect. So what is the meaning of non-Markovinity? The non-Markovinity is basically any open system, which is basically a system which is talking to its environment, can have two kinds of evolution, Markovian or non-Markovian. And non-Markovian evolution is the more standard one. It's the evolution when your dynamics depend on the previous history. That is literally the meaning of non-Markovinity. It's also sometimes called entanglement in time. It's as if the system's future is entangled with its past. And of course, this is not about causality. Of course, there's causality even in Markovian physics. But when we say non-Markovinity, it's not about just the previous step, but the whole history matters. And the standard signature of non-Markovinity in open systems is what is sometimes called information backflow. Information backflow means that typically when you think about noise acting on the system or environment coupled to the system, there is a one way, the system can only lose information to the environment. But in non-Markov system, the information can flow back into the system. This is sometimes considered the typical signature of non-Markovinity, that there is coherent information backflow from the environment to the system. It is detectable in system evolution of system observables like time, but the problem is that it's usually these effects are very weak and very short-lived. They are in the small like transients or fast transients at slow times. So and plus this information backflow and how to think about non-Markovinity, that itself is a question of debate amongst theorists, and it also has implication for experiments. So one can think about, like, when you look at least these two bullet points, that the fact that they are weak and then they're short-lived, why should we care? The reason we should care is that, first of all, there was this recent work by IBM, where they actually showed and studied how non-Markovian errors can lead to off-resonant coherent gate errors. So lots of randomized benchmarking protocols and how you think about gate fidelity and or the GST protocols, gate set tomography, they all assume that your errors are uncorrelated, which essentially means that it should not matter when you do the gate, it should always have the same error. And these kind of non-Markovian errors are very insidious in that sense, because they break the stationarity assumption. Because now your error will depend on when the operation is performed. It's not the fact that you can just concatenate gates at some time, but now the position of those gates in your time sequence will also matter. So that's a really troublesome problem, because that basically takes away our control from trying to understand if these errors can lead to crosstalk between the errors at the gates performed at different times. Then that is much harder to correct. And in fact, most of the error correction protocols, be it Shor's code or Steen code or any or CSS codes, the general Calder-Bank-Shor Steen class of codes, the stabilizer ones, they actually assume temporally and spatially uncorrelated noise. At least most of them. There have been like a couple of subsystem codes which have been proposed in the recent years, which do not assume that. But most of the error correction protocols assume almost Markovian noise. They don't assume any temporal correlation. So the common ways, so like this is an example I was trying to show you, that like saying that it's weak and short-lived. So this is exactly the excited state population of a qubit coupled to a lossy cavity, and we are just looking at its decay. Now, if you do a genuine regular Lindblad master equation simulation, or just like calculate it in your Mathematica using or use QTIP, you get the red curve. But if you actually do the full simulation of the system, which is the qubit and cavity, you don't truncate the cavity, and you also make a non-Markovian construction, let's say bond-web field is a typical non-Markovian equation, you actually see at the initial times there are actually these oscillations which are not captured by Markovian evolution. So this is why the non-Markovian common measures of non-Markovity, they are trying to capture these short time transients. This is the signature of non-Markovity. The fact that you don't get red, but you get blue, that is the signature of non-Markovity. That there's some kind of a back and forth happening. It's not monotonic decay. It goes down, but then it comes back up, and then goes down and comes back up. So something non-monotonic in time is happening about the system. And the problem with these kind of measures are that they require a reconstruction of the full system state. Typically, at each point in time, you have to reconstruct your full qubit state. So you have to do state tomography. Plus, you have to do this tomography with a fairly sufficiently high bandwidth, because you're trying to capture this as a function of time. And then to make matters worse, this kind of measures, like this is the most famous non-Markovian measure. It's called BLP. BLP is actually the initials of three famous theorists, Breuer, Lane, and Pilot, who gave this non-Markovian measure. This kind of measure also requires a maximization over the entire Hilbert space, which essentially means that you would have to prepare your system in several initial states, and then take those initial states which lead to maximal this kind of recurrence, and then trace the density matrices distances. This is a trace distance problem over those. So it's a really horrible, from an experimental point of view, measure. It works but it does measure information backflow. So we were thinking that okay, this is not working. This is not absolutely scalable. And plus it gives you zero physical intuition of what is going on here. What is this strange non-Markovinity? So we wanted to see, can we define a signature of non-Markovinity which persists its long times, so that I don't have to do this very short measurement, very short time fast bandwidth measurement, because this is very expensive. And can we actually do something which is directly experimentally observable without some tomography? because tomography is extremely expensive, especially when you have to do anything for multi-qubits. And then we were also talking to our field theorist friends at that point, and they were like, yeah, good luck trying to ask a field theorist to do any kind of state reconstruction. These kind of things can happen for qubits, but cannot happen in other areas. Whereas the idea of non-Markovinity is cross-cutting. It doesn't only happen in quantum qubits, it happens in all quantum systems. So we wanted a universal measure which can be experimentally observed. So so this is what we've actually calculated. This is an analytical calculation. We are using the same system I was showing you earlier, a qubit coupled to a cavity with some coupling and some decay on the cavity. And now, as I said, this if you are able to see my cursor, this is the master equation of just the qubit. I should have probably written it in blue. This is not for the full system. This is just for the qubit. So it has some kind of its own Hamiltonian and decays and all that. So that is this is the internal intrinsic qubit dynamic. But then, as you can see, because the G square induced dynamics because of this cavity, because there is an open system now, which I am actually simulating using a cavity with a decay on it. This actually has the whole history of the qubit. This S goes from 0 to T. So this is a really time non-local kernel, which is actually deciding what the qubit state will look like at time T. It depends not just on time T on this side, but on the whole history. So using this, one can calculate, let's say, what is called a 2-point correlator or the Green's function. And then when you take the Fourier transform of the Green's function, you actually get what is called the qubit spectrum. Now here, everything is time dependent, including the rates. So the spectrum looks complicated, but I have written it in the form which should remind you of a Lorentzian. It should look like a Lorentzian, but it's not really Lorentzian, because in a Lorentzian spectrum, these guys should be independent of frequency. But here they are functions of frequency because of non-Markovinity. So now if I would have measured the same guy, same way, I would have calculated the same emission spectrum of the qubit. So this is just like, doing spectroscopy on the qubit. I should have seen a dashed line, but what I find using this non-Markovian construction, which we actually call frequency domain, we actually use a special trick, which I don't have time to go into. We actually solve the master equation not in the time domain, but in the frequency domain, which makes it much easier to include the memory. We actually find the solid black spectrum. So you see that there is this extra side peak which appears, which your Markovian calculation does not show. So what is this center peak? The center peak is what you actually expect, the lamp shift of the qubit and the decay of the qubit and so on. But this side peak is as if it actually, when you look at it, the real and imaginary part corresponds exactly to the Green's function of the cavity, not the qubit. So it's as if that you are looking at the cavity through the qubit. So in some sense, this is reminiscent of, like, if people have seen strong coupling, you have an avoided level crossing. But this kind of this is the analog of that avoided level crossing, but in a very far off resonant regime or weak coupling regime. So this is not, system is not weak, strongly coupled. It's weakly coupled but it still has this side peak, and this side peak is because of coupling with the to the cavity. And this will not, you will not capture this, because unless you do actually a full history of the qubit inclusion in your physics. So based on this very evident change in the spectrum of the qubit, we thought, okay, well, then why should we do tomography? We should just use spectrum, because experimentalists are extremely good at measuring any kind of spectroscopic quantity. We quantified the difference of the spectrum of these two spectra using Kullback-Leibler divergence. This is sometimes also called relative entropy. So the idea is the following. If you think of these two spectra, the dash and the solid spectra, as two kinds of probability distributions, Kullback-Leibler divergence tells you that what is the error you make when you confuse one probability distribution with another. Which means, let's say that you were doing some random process and you had some P of X, like some random number had some probability distribution. And then there was some other random process which had the probability distribution Q of X. Kullback-Leibler divergence tells you how much relative information you lose or how much entropy you gain just because you thought you had Q, but actually you had P. So that is essentially the idea of the Kullback-Leibler divergence, where we are thinking of the spectrum as a probability distribution in frequency space. And we are saying what is the information cost of making the Markov approximation per unit bandwidth of the qubit. So that I can explain more why later in the questions if you're interested why we did that. But the idea is that we are trying to basically say, think of spectrum as basically, which is actually what spectrum literally means, that what is the probability of the qubit emitting at the particular frequency that's given by the spectral density. And now, if you try to make a Markov approximation, you will lose this much information because your actual spectrum is black, the solid black. And if you think it is dashed black, this is the amount of information you will lose. So the advantage of this is that it eliminates the need for any high bandwidth measurements because we are actually measuring a steady state spectrum. It's really completely observable. And importantly, what we are trying to, if you can probably, hopefully it's clear from the explanation, we are trying to quantify the deviation from Markovianity. We are not trying to say what is non-Markovianity. We are saying what is not Markovian is non-Markovian. We are not appealing to an information backflow or some special physical effect. Anything which is not Markovian is non-Markovian. Actually makes sense. It's almost tautological in its logic, but it's true. So now we using this, we actually applied this to the qubit cavity system with the cavity in its thermal state. We expect like some thermal photons in the cavity. And you can actually see this waterfall plot, which is plotted where we are plotting the spectrum as a function of detuning over kappa. And then you can take, you can calculate this, this measure NS as a function of kappa and as a function of delta. And what we find is if there is large detuning, you have a very strong non-Markovianity, which means if the system and environment or here the cavity are very strongly detuned, you should expect strong non-Markovianity. Just because you're off resonant, you should not think that your memory effects, which from the cavity to the qubit coming back, will not be important. And however, if the cavity has very large kappa, which means it decays excitations at a very fast rate, then it's very weak non-Markovianity, which also makes sense intuitively, because for information backflow, the cavity has to retain information for some time. And if it's not able to retain information because of its large line width, then that information is not going to have any impact on the future evolution of the qubit. So that is why large cavity line width, actually we find it, the exponent is 2, it leads to weak non-Markovianity. More interestingly, what we found was, what if I actually put squeezing on the cavity? I can also squeeze the cavity. So it means the cavity has some kind of correlations. And so this is the waterfall plot we find. You actually start from this point. This point, like you actually have a non-Markovian spectrum for a given detuning. The delta is fixed between the qubit and cavity. And then you start squeezing the cavity. You start increasing R. And you can see actually now it's almost as if you get this blue spectrum in the middle for some particular value of R, which essentially means if I just take this cut along this line, and also NS versus squeezing, don't worry about delta tilde, it's just a way of parameterizing squeezing, the effective detuning because of squeezing. You find it actually dips at a particular value of R, this particular value of R. So in fact, the fact that your system, the environment can have correlations, in this case, it is Gaussian correlations because your cavity is squeezed, can actually make your system forget. The system usually remembers, but for a particular value of these correlations, the system, you can make the system forget its past, which was very interesting. And we thought it was actually quite unexpected. And then as a final thing, this is my final slide. We actually made some comparisons with the BLP non-Markovianity, which is basically this time domain recurrence measure I showed earlier. And you see for certain values, so this is the case for the thermal bath, we actually found that BLP only looks for information backflow. It has a very particular interpretation of non-Markovianity. It says non-Markovianity means some coherent information is happening, whereas we are not doing that. We are basically saying anything which actually leads to a deviation from what you expect from your Markovian spectrum is like confusing it with a non-Markovianity. And that's what we plot here. And you can see that therefore BLP sometimes gives you false negatives. The Markov non-Markovity is actually there, but BLP is not able to detect it. But our proposed spectral measure is able to do that. But there is an even worse problem, which we found, and this is actually a false positive. So this line, which I'm showing you, is for a squeezed bar. This is for a squeezed bar, where I'm plotting the non-Markovinity calculated using this BLP measure as a function of squeezing. And you can see that it starts saying, it shows that it keeps increasing up beyond a certain point, right? This delta is that squeezing induced detuning. And amazingly, this whole simulation was done assuming Markovian squeezing. There was, by definition, we put Markovian squeezing, and BLP still said, oh, no, the system is non-Markovian, which is impossible. This was just a Lindblad equation with squeezing type dissipators coupled to a qubit. So it actually misdiagnoses oscillation due to Markovian squeezing. And you can see the spectrum. I'm showing spectrum at different parts. This is the emission spectrum of the qubit. You can see there is no side peak. It's actually a single peak. So actually, when you calculate the spectral measure, that's always zero. So in fact, not only BLP gives you false negatives, it can also give you false positives. So if you try to really take this to heart, that any kind of non-monotonic behavior in time is non-Markovinity, one has to be very careful. That's not necessarily true. And this is what we were able to find using this spectral measure, which I showed you earlier. So with this, I think I will just stop. I hope that I have given you a brief taste of what we are thinking about in terms of now out of equilibrium effects in these circuit QED setups. It's a very powerful platform to study both these non-QND and non-Markovian effects. And they have direct implications for several error correction protocols. And now we are actually trying to see, okay, non-Markovinity can even detect correlations. So what about many body correlations, like you find at a quantum critical point? So there are lots of opportunities of applying these ideas to not just quantum information, but even in condensed matter and field theory. So with that, I'll thank you for your attention and take questions.
Professor Arjun Kamal, thank you very much for interesting presentation. I think they learn a lot and get new perspective. And we have two questions actually I want to ask. Can we get the spectrum of qubits of cavity green function on time domain using master equation of qubits?
Yeah, so if I repeat the question for my understanding, you are saying, can we obtain the spectrum from master equation?
Can we get a spectrum of qubits of cavity green function on time domain using master equation of qubits?
Yes, the answer is yes. That is exactly what you can do. You can actually calculate the 2-point correlator or the Green's function from the master equation. But as I didn't have time to say this, what happens is in the frequency domain, so actually I don't know if people are aware of Fourier transforms. So this looks like a very time non-local equation, but if you actually analyze this equation in frequency domain, this is actually a frequency local equation. What that means is that if I take a Fourier transform of the full equation, I actually get there is no non-locality left, because anything which is time non-local is frequency local. So using that, you can actually calculate the Green's function directly in the frequency space also. You don't have to go through this path of first calculating the Green's function in time and then taking its Fourier transform. What I'm saying is you can go directly from here to here. It's possible. I just didn't have time to explain it, but yes, you can get it from master equation.
Okay, thank you very much for your answer. Another question is, Professor Arjuna, you mentioned that Markovian physics follow causality. So is there a practical application of Markovian physics in terms of time? Just a hypothetical questions.
Sorry, can you please repeat the last sentence? Is there a particular application of
is there a practical application of Markovian physics in terms of time?
Yeah, so I think the way the one way of thinking about Markovinity is actually a very special approximation, and it actually works for circuit QED like setups, because at least for few qubits, because we expect that our noise has no structure. It's very flat. It's called this is called the white noise approximation sometimes. But actually, when you go to multi-qubit setups, what happens is that you have, and this is the problem, this was the point of the IBM, that you can actually you might be doing some quantum operation on one of the, let's say let's say you have a 4-qubit chip. You're doing some quantum operation on qubit 1 and 2. But so the 3 and 4 are called spectator qubits. But the spectator qubits will change depending on 1 and 2. These kind of errors are actually called off-resonant coherent errors. They're off-resonant because, sure, this can actually happen even when all these things are different. And they are coherent errors because this is not necessarily just some incoherent noise acting on your qubits. It's possible that, like, just because you let's say that you do a C naught on qubits 1 and 2. Because of that pulse, which you have put on 1 and 2, can stark shift your qubit 3. Just because there is some electric field. Okay, it is off resonant, but can happen. That can lead to some kind of coherent error. So in that sense, I would say that non-Markovity is actually the default. It's always present. We have to understand it, whether we have its application or not. Though there have been some applications where people have shown that if you use non-Markovity, you can actually speed up certain quantum processes. But it depends on the exact quantum process in question. But I would say that it's not just about applications, which are obviously interesting. We have to understand this because, first of all, it is actually the whole truth. Markovity is just an assumption. And secondly, as we keep making our quantum systems bigger and more strongly coupled and faster control, we are actually pushing them in a regime where Markovian assumption is becoming worse and worse. And that's what these guys showed in this paper. So that is the reason we wanted to actually have some way of thinking and measuring deviations from Markovianity, which is experimentally tractable. That makes sense.
That's right, really. For many body physics, I think, since I am also interested with open quantum systems. I want to ask that I think you focus on correlation between
Yes.
2 point in time, right?
Yes.
If you can extend this more complex scenario involving in multiple time point, I think it will be great achievement for understanding dynamic in quantum physics, quantum system, especially for quantum chaos, I think, and entanglement.
Absolutely.
It
That's
will be
actually
great to
an
know.
excellent point. Yeah, I completely agree. Actually, that's a very, very good point. This is something which we are actually now thinking of applying to, as I said, over towards the end. Like, you can actually think about phase transitions, but as you said, as you're pointing out, you can also think about dynamical transitions. You can see from transition from chaos to integrability. And you can see how these kind of two-time correlators, what kind of spectral signatures they give, whether your environment is chaotic or integrable. So yes, there are lots of interesting places where these kind of ideas can be applied to. I agree.
Thank you very much. I will follow you. Professor Arjuna Kamal, thank you very much for your time, answer all questions, and that was really great lecture. We gained a lot new perspective. Thank you very much.
Thanks very much for hosting me. Thank you.
Okay, everyone. Now we will be with Dr. Mariam Bautista Journey. Let me introduce her. Dr. Mariam is a computer system engineer at Lawrence Berkeley National Lab. Her research interests spanning analog, digital, and mixed signal integrated circuits, VLCI, and ASIC design, RF circuits, as well as superconducting quantum circuits and logic. Before her current role, she was a postdoctoral researcher in computer architecture group, where she contributed to several projects, including the superconducting trace logic accelerator, test and evaluation for IRPA's Super Tools program, ASIC implementation and verification for Project 38, and cryogenic control for quantum application. And today she will present on superconducting digital computing. Dr. Mariam, happy to have you here, and we are ready for your lecture.
Hello, thank you. Good morning, afternoon, and evening to everyone. I think we're around the globe, so it's morning here in my time. So I'm based in Seattle. So good morning, everyone. Thank you so much for inviting me to this talk. And let me just share my slides before. Can you see my slides?
Yeah.
Okay, great. Let me do the slideshow first. All right. Hello. Good morning, everyone. So my name is Miriam Gay Bautista. I'm at Lawrence Berkeley National Laboratory, and I'm also with Romanium. So I've been with volunteering with Romanium for quite some for a year now during the quantum program. So I think if you attended Romanium, you also know me from the team. But yeah. I'm happy to be here with you to talk to you about my research at Berkeley. And let me just charge my computer so it's getting a little bit, okay, sorry about that. So I'll talk about superconducting digital computing. So it's a little bit different. It's not too physics heavy, but a different level of abstraction. It's more of the different models of computing and how we could use this one to advance quantum technology. So the outline of my talk, I'll give a little bit of introduction on Moore's law. So, and what are the different factors of considerations and in technology scaling trend, and then what are the new models of computings and alternative computing, and then I'll give an emphasis on superconducting digital computing and its potentials, and I'll talk about our effort in developing new models of computing which is based on temporal domain, and lastly, I'll give an overview of the potential of the superconducting electronics and computing for quantum applications. So many of you have known Gordon Moore. So he's the co-founder of Intel Corporation. So he's a great engineer. And in 1965, he published a prediction, a historical trend that the number of transistors in a dense integrated circuit doubles every 2 years. And this advancement is important for other aspects of technological progress in computing, such as processing speed, power, and cost. So his predictions remains true for about 50 years, and it serves as a driving force behind the semiconductor industry revolutions. And Moore's law has been greatly driven by photolithography process. And we have been moving steadily into smaller scale at the exponential rate. And the benefit is evident in the performance in energy efficiency. But as we scale down, we are going towards closer to the size of the atomic atom or atomic of the atom. And due to the physical limitations and exponential growth, so due to the physical limitation and exponential growth in cost, so contrary to the popular claims that Moore's law appears to be it's not even valid. So we tend to ask, is Moore's law still valid? So while the number of transistor is no longer doubling every 2 years by definition, it's still delivering exponential improvements, however, at a slower rate. So we need to think of the different models of architecture, so new chip designs, new materials, and so there are a lot of efforts gearing towards improving the performance of technology. And yes, so we have to think of these new models of architectures in order to still continue to deliver the performance for future technology. And here I'd like you to talk about the technology scaling trends. So what you see here is a graphical representation of technology scaling with respect to the performance versus year. So from 1975 to about 2010, you will observe here that the growth in you will see the growth in performance, integration density, power, and efficiency. But in 2025, in this part here onwards, what you will see that starts to flatten out. So this was a projection by Conil and his colleagues, and they made a study on the actual scaling of the top 520 supercomputers. So it's not really flattening, it's just that it's scaling slower as compared to the previous years. So the question is, what are we gonna do next in order to address the demands for a better and advanced performance? So in the semiconductor industry, there are different methods on how we could scale down our transistors. So one is geometrical scaling. this refers to the reductions of your gate size of your transistors. Equivalent scaling, when we wanted to scale or reduce our transistor in a vertical manner, footprints in a vertical manner. And the third method is to do the 3D integrations, where we stack multiple sub-circuits on top of each other, and by doing so, we're able to reduce the footprints. And so it's been 50 years of technology scaling with Moore's law, and there are other ways to continue scaling. And we need to come up with some new devices, new transistors, and new models of computations. So if we can scale in terms of photolithography process, then we need to study the new models of architecture and new packaging. And this becomes more efficient maybe in 10 years' time. But beyond that, we also need to think about the new effective devices and materials and new fabrication. So, of course, new model of computations, like here, what you see, there's new devices, spintronics. In the new models of computations, we have neuromorphic computing, we have quantum computing, which is our main topic of a workshop. We have analog computing, adiabatic computing, and for new models of architecture, we have superconducting circuits. We have a system-on-chip integration. So all of these are different models of computing. So I'll talk about here, I'll give emphasis on superconducting circuits. I know we use superconducting circuits to implement our QPU, but there's also a different model of computing that we could use superconducting circuits, and that's what I'm going to talk about. So superconducting electronics is the phenomenon where we observe some materials when cooled below its critical low temperature, like approximately Kelvin, will exhibit a zero electrical resistance falls to zero. That means there's a current flowing, but there's no voltage. And if you can see here in the graphical representations of superconductor versus the normal metal, at superconducting state, the magnetic field will expel. And so their energy dissipation is drastically lower as compared to the standard, actually CMOS. So even after accounting for cooling. So using the superconducting material, it offers the promise of an order of magnitude higher speed, better energy efficiency than the transistor-based system. And when we use superconducting digital computing, it also promises an alternative to preserving performance scaling after the traditional CMOS scaling ends. So at microscopic level, let's talk about this at macroscopic level here. So we classified superconductor electronics, which is classified as passive or active. So we have two classifications, passive and active superconductor components. So active superconductors are constructed using Josephson junctions, which is made of two superconducting materials sandwiching with a thin insulating barrier. So in data processing, the information is stored as a magnetic flux quantum. So it's the presence and absence of your magnetic flux. And Josephson effect is the phenomenon where the current flowing indefinitely without voltage. So it is where the electron pairs tunnel through the wire without a resistance. So one of the most important parameters of the Josephson junction is its critical current. So this is the maximum superconducting current capable of flowing through your junction. So where your junction can be switched from superconducting state to a resistive state by increasing the amount of current above your critical current. So the transition to resistive state allows the change of your magnetic flux in a superconducting loop, and hence we can perform digital logic operations. So one of the popularly known use of SFQ logic is so there's a different family of SFQ logic. So SFQ logic is so in SFQ logic, the information is represented as a magnetic flux quantum pulse. So in logical bits, it is where the presence and the absence of pulse. So when we do computing classically, you have your binary bits, which is like represented by state 1, 0 with state 1 and a state 0 at 0. So it's 1 and 0 computations. We could use the same dynamic in superconducting SFQ logic, but we use different models of how we represent our information. So it's based on SFQ pulses. So an SFQ pulse is produced when a magnetic flux in a superconducting loop of inductance changes by one flux quantum. So as a result of your switching. And in superconducting digital logics, we use also known as the magnetic flux quanta. It is used to encode, to process, and transport your data informations. In SQ logic are made of active Josephson junctions. So what you see here is just an example of the circuit architectures. So you have your passive elements like inductors, resistors, and transformers. And if you could see that the architecture of the circuit is quite different from the way we see circuits in CMOS. So the use of Josephson junctions, a switching element in digital circuits, have attracted a very significant attention due to its high switching speed. So the switching of this SFQ pulses in the order of 2 picoseconds. And that would, because of the fast switching speed, it actually shows about 10 to 100 times faster operation compared to CMOS-based system, and 10 times lower active energy than CMOS. So here is just some example of how we implement our logic in CMOS, right? So we use NMOS, we have PMOS, and then we combine these circuits to create a logic gate. So here you have an inverter, you have a NAND gate and OR gate. So from basic logic gates, we can create a little more complicated circuits like a half adder and a more complicated circuits of like arithmetic logic units here. So you can combine a lot of logic gates, and then you can create a more complicated system that allows you to do computing. Similarly, we could also do the same dynamics in superconducting logic, but our circuit architecture is totally different. So here we make use of a Josephson junctions. So the architecture, for example, of your NOT gate, which is similar to the inverter in CMOS, is something like this. So you have a Josephson junctions and you have your inductors. So we actually play around with the amount of current that flows into your magnetic loops here. So a NOT gate is like there's no pulse, or it's gonna be in a state 0 when there's a pulse enters an input. And if it's a state 0, then an output a state 1. So similarly to the OR gate, when there's both SFQ pulses in either A and B, that would give you an output of a state 1. And like AND gate, similarly, the dynamic works on how we do it in CMOS, but the architecture of your circuit is different. So you can see here, that's the this is how we implement our AND gate in SFQ logic. So there are also different other logic gates. So in superconducting circuit, because we input our data in DC base, we have to convert it into SFQ base. So you have your interfacing cell, which is what we also call a DC to SFQ. And when you convert your SFQ back to DC, then you have another, I don't have it here, but 2 of the interfacing cells that we use is the DC to SFQ circuit and SFQ to DC circuits. Another difference with the CMOS base and the SFQ basis, we also have interconnect circuits. So interconnect cells are used to connect 2 different logic gates. So you have a mergers and a splitters. We also use buffer cells, like when we wanted to store or delay a signals, we can use a data flip-flop, and this is how data flip-flop, and an NDRO, basically use NDRO for switchings and storing, putting some delay into your circuits. And here I'd like to talk about the one of the projects that I work with in our team. So we actually, our team with Berkeley Lab, together with our collaborators from UC Santa Barbara, we work on developing a new model of computing based on temporal encoding. So in race logic, we encode data values based on the time domain. Well, we're familiar in binary that we encode data based on the voltage of each rising clock, right? So in race logic, we map the data as it arrives. So here we have different types of race logic implementation. So we have a unary, for example, if you have an 8-bit data, you represented each bit by one slot. And we have a unipolar race logic, which we can create values between rangings from 0 to 1 to represent an 8-bit. And also we have a bipolar race logic which range the values from -1 to 1. So when you do computing with and negative integer number, so we use a lot with bipolar race logic representation. So this is for negative. And so there we have a couple of papers with our project on race logic accelerators, and you can I'm not go one by one, but you can actually go and look more into more details of this. And one that so the significant output of our research is that in temporal domain is the temporal computations mitigates superconducting with low density, and it enables you to reduce energy. So that means your circuit is more energy efficient. And because the circuit is energy efficient, then we'll be able to scale it and do more energy efficient computing. So we have DNA sequencing, NOC is a network on chip. You have an FIR accelerators and an FFT. So FFT is very important in signal processing. So for example, if you build an FFT circuit, your FFT must be able to do some sort of computations. And in your FFT, for example, your computing means like if you want to multiply an X and Y, you need to build a circuit that would be able to do multiplications. So we build so you have to create a multiplier, you have to create an adders or accumulators. So we build our multiplier using NDROs and mergers. This is like the high-level block diagrams that you can implement your multipliers, a bipolar multiplier, so you'd be able to do computing with negative numbers. And here is also your accumulators. So we represent accumulators as an addition, so where you can add your signals. So here you have your, we process FFT signal using a Mach unit, which is a multiply accumulator units. So and that's how you can read more about the papers, and then that's how we do computations. We create circuits that be able to multiply and do additions and other computing. So these are just some of the examples of superconducting chips that have been fabricated and published. So you can read more about how to build an RSFQ processors. This is the superconducting SFQ logic base. I think this is the highlight of this processor is to be able to do fast digital computing at 100 gigahertz. You could this is an example of an 8-bit parallel arithmetic logic units. So ALU allows you to do mathematical computations like subtractions, multiplications, additions. And here also you have an example for a converter. So you can process convert your analog signal to digital signal and vice versa, digital signal to analog signals. And there are also different actually families of SFQ logic. So we have AQFP, which is based on adiabatic quantum flux parametric. So it's also a different circuit architectures. We work a lot, our project work on temporal domains, temporal SFQ. And then there's also other alternative, which is an QPSJ, which is quantum phase shift junctions and negators. So there are different families of your SFQ logic, SFQ logics. And so here, so you can see here, actually in CMOS, before they actually concluded that CMOS is the best, prior to that, there's have been a lot of research was conducted in search for which one of the winning combinations, and it's actually in the late 1980s, then they able to identify that the combination of PMOS and CMOS is an efficient way to create logics. And similarly, so superconducting logics are actually not old. I mean, it's pretty new. So there's a lot of going the families of RSFQ which just started to came out in 2010s, and so RSFQ is one of the popular ones. So in our circuit implementation, we use a lot of RSFQ and ERSFQ, and these are some of the families of SFQ logic circuits. But there's not much. There's still not in the applied superconducting community, there's no winning families yet. So all of these SFQ still be able to do computing, but they have not identified which one is really more efficient. But all of this SFQ family has its own advantages and disadvantages. And the way we do some of the considerations when we evaluate our circuits is its performance, its power, the cost of the designs, and the compatibility of this SFQ family with the other technologies. Like if we wanted to create an heterogeneous integrations with the other technology, what we can combine like SFQ logic to the other like a CMOS-based logic. So we have to think also how compatible this technology with the other existing technology. So here, so SFQ applications, there's different areas of applications. Mainly it's market driven. So you could use it on optimizations, media, sensors, and also one of the popular is the use in quantum application, which is in qubit control and readout. Let me see. So yeah, I'd like to next I'd like to highlight the potentials of the superconducting electronics for quantum applications. So the applications of the superconducting electronics primarily has potentials in the interfaces of your cryogenic computers to the outside world. So the implementations of micro-Josephson junctions in superconducting, the implementations of an SQ-based qubit, SFQ-based qubit control and readout. So this provides the classical counterpart and how we process information after the computing done with your qubits. So, and it provides an advantages because of it's a low power circuit. So we will be able to do a high performance SFQ-based data processing. Like after you qubit, then you have to process your data. You need right now, we still need a classical circuits to process all this data, and SFQ AD converter and SFQ-based decoders. And so if we look at our current system implementation, I have here as example, it's the IBM computers. So it's a big system. And so you have here at the outside of your fridge, you have your control and readout, where your user do all the manipulations. And then you have all your microwave electronics and control systems, and then the signal goes to your dilution refrigerator. And so if you look at here, this sides, your control and readout and your microwave electronic systems, this is actually quite big and bulky. Now we'll try to think on how we could actually make the system more efficient by being able to, can we actually bring this, system inside the fridge, or can we do this control and readout inside the fridge so that we could create a more compact quantum system? So there are two different types of controlling our QPU, right? So one is an analog-based control where you use microwave signals. So you have from the users, you send out your signals, and then you have your analog to digital converters, and then the signal goes to your qubit. So here is just an example of an FPGA-based control platform. So one is developed by KIT, it's in Germany, and the other one is the Cubic, which is an open source FPGA-based control and measurement, which is developed in an AQT lab at AQT at Berkeley Lab. So the way they process the information is you have your data processed in FPGA, and then it goes to a conversion using analog to digital converting, and then you have your RF conditionings that do the bandpass filtering, and then the signal goes to your qubit or in your cryostat. So the trade-off of this kind of like system is the system is quite complex. So there's a large I/O, so you need a lot of wires from the outside, goes to your QPU, and then so your I/O system, if you can see, there's a lot of like here you have a lot of input and output wires, and that makes your system a little bit bulky. And because your information has been processing outside and then goes back to the fridge, so the back and forth flow of your information signal, that's also create a very high latency, and the system is quite expensive. And if you continue to have this system, it's actually difficult to scale. So we have to think of other way on how we could efficiently control our qubit. And there's a lot of efforts ongoing with using cryo-CMOS-based quantum control. So taking the advantage of what's existing with the CMOS, so they implement a quantum control chip using CMOS that operates at a low temperature, so at around 4 Kelvin or lower. So these are just some example of the cryo-CMOS chip that does quantum controls. Another way of doing control is using a digital base. So a digital SFQ-based control superconductor. So in this manner, we are able to do to drive your qubit using a digital base control. So it's actually using an SFQ pulses sequence to drive controlling the your, like for example, the rotations of in your black spheres. So we use SFQ digital signals for that. So other than the signal, there's also a lot of application for FSU. So you can create an SFQ-based co-processing unit that allows you to do the control and also do the decoding of your signal. So you can put that in a level here, like a few layers above your qubit, maybe around 3 Kelvin. And you could also create an SFQ-based repeater signals, and you could put it down lower, which is more closer to your quantum processor, probably around in 0.1 Kelvin. And so by doing so, we're able to bring in your control electronics inside your fridge. We're gonna get rid of all this bulky stuff, and then it's become more, your system become more compact and more efficient. So this is so we bring out your control and rather closer to your qubit. And so what's the advantages of this? So this is let me see. So this is the proposed hybrid superconductor semiconductor electronics for your cryogenic system. So you can bring some of your computing circuits around below 4 kelvins, and you could also bring it down more closer to the qubit at around 20 millikelvin using single flux quantum. So in this implementation, there's still a lot of improvement. So this is still a big area of research, because by this implementation, there's still relatively slow reset timing capabilities. The size of the devices are still big, and further optimizations in the switching design and also the superconducting material. So it's still a lot of improvement on how to really fully bring the control and radar closer to the qubit. So in Berkeley, so we try to have this the current implementations of some of the experiments here. So we use Cubic, which is an open source FPGA-based control and measurement. So you can read more about this one. So they have actually, it's open source. If you're wanting to play around some FPGA, you can search that one online. And they also create Quasar, which is a RISC-V5 set architecture co-processor unit. So here, So it's still the control is still done outside your fridge, right? So one of the effort that we're trying to do here is to, since we try to bring it down in a level we're close to the qubit by implementing using RSFQ. So all of this mechanism is implemented first in FPGA. Once it's validated, and then we create those submodules in SFQ domain. Sorry about that. So we try to bring, so right now, if it's implemented in FPGA, it's been tested and validated. So we bring it down in a cryogenic implementations by designing it in an RSFQ or using AFQ logic. So here, this is the block diagram architecture of the AFP controls, and what we try to do is to recreate all the submodules using SFQ logic domains. So this is just some of the examples of the generated circuit been layout. Sorry, my throat is itchy. Let me drink some water. Okay, so from this, we try to bring out and implement using SFQ logics. And this is just some example of these circuits. And another thing that I like to highlight, because there's one company that I've known that's really done this one, and I think it's one of the most advanced in terms of the implementations of SFQ in quantum applications, is SEEK. So if you, I think they were at the Womanium program, they had a talk with, and then they presented also their implementations. So this actually the quantum to digital converter is the one of the most advanced, and I really like their implementations. So what they call it the DQM, it's a system on chip. So they implement these controls and read out actually locally. So they have the qubit, and this control signals is actually implemented right on top of your qubit. So this chip is able to do phase detections. It able to convert your output signal to digital SFQ data. So you have your SFQ clock, and then the output in SFQ data, and then they also have an SFQ coprocessor unit. So they are able to do all the controls and processing locally inside the cryogenic fridge. And I think so it's still patent they said it's patent pending, and I think this is one of the most advanced right now implementations of an SFQ based control and read out chip. So I encourage you to look at more in details the architecture, and it's really it's a good one. And so yeah, in summary, so the combinations of so we still need a lot of classical actual electronics and circuitry to process a lot of our quantum systems, right? And the use of superconducting electronics and digital logics has an advantage because it's the compatibility in the operating temperature, the compatibility in energy levels, and the compatibility of materials. And by doing so, we're able actually to bring down the data processings, error corrections, and control and read out closer to the qubits by creating a superconducting coprocessors. And moving forward, there's still a lot of things that need to be discovered and explored in the field of superconductors and quantum technology. But I think, so I've been working in superconductors, and I think there's really good potentials in using superconductors to advance more quantum, your quantum system. But of course, there's still other implementations. But we still don't know yet which one works the best, right? So it's still a lot of research ongoing on. And I'd like to thank the team also that I work with at Berkeley Lab. So these are the people who work on the superconducting logics. Yep, and yeah, thank you so much for your attentions, and I'm open for questions.
Thank you very much, Dr. Mariam, for such a good presentation. We have one question just. The question is, which quantum control is more efficient, CMOS or digital SFQ, and why?
Sorry, can you repeat that?
Sure. Which quantum control is more efficient, CMOS or digital SFQ, and why? Which one?
Oh, so CMOS base, some of the implementation of CMOS base actually they started at 4 Kelvin, and then they tried to go down more in the lower layer. And CMOS control works, but I think there's still a lot of effort on how to bring CMOS down in a lower temperature. So the advantage of the SFQ and superconductor base is you could actually put it down closer more to the qubit. So both works. The implementation both works. You could do control and read out, but I think there's a little bit of difference in how you could actually bring down the chip on the level that's closer to the qubit. And I think for the current implementations, the SFQ-based circuit is where we could bring it down closer more to the qubit, and that's its advantages.
Thank you very much for your answer. Actually, we have another question. Could you please explain CQS QC control system a little much?
And sorry, can you explain what?
SEQC control system.
Oh, this one. So yeah, so this is six. It's a data sorry, not data. Digital quantum management system. So what it does, you can able to do the control and process your control and read out locally. So if this is your QPU, you have another co-processing unit, which is co-located near to the qubit. So it does your controls. You can actually send the control signal closer to the qubit in a very close proximity. So and that's what it does. So it operates at 20 millikelvin. So all the control signals. So in an analog implementation, you have your control and microwave signals implemented outside your cryogenic fridge. But what they did is they bring out the control closer to the qubit, which is in-house now in your fridge, and that's what its function. So it does the control and read out of your signal locally, and that's one of the I think highlight of this in their chip is it's in-house.
Okay,
Did I answer the question correctly?
Yeah. Thank you very much, Dr. Mariam, for your great presentation and informative lecture. I think we have no any